Okay, so now we're getting into, I believe it's section 9, looking of chapter 16, looking at kind of what relationship salt, so when you dissolve a salt or you have like an anion dissolved in solution, how they behave. So anions, when you dissolve an anion in water, they behave as bases. So as such, they can react with water in a hydrolysis reaction to form OH minus and the conjugate acid. Um, so your X minus there represents an anion, so some negatively charged substance, and that can interact with water to pull a hydrogen off, potentially, and then to produce more OH minuses, so creating a more basic solution. Okay? So you're producing more OH minuses. So then let's talk about the cation piece. If you have cations are positively charged ions, typically kind of the remnant, like let's say you dissolve sodium hydroxide. But if you have a cation there, cations with acidic protons, so like ammonia here, NH4 plus, will lower the pH of a solution. Most metal cations that are hydrated in solution also lower the pH of solution. So a metal cation, whether it's Na plus or aluminum 3 plus, will lower the pH, make it more acidic in the process. So anions make things more basic, and cations make things more um, acidic. And the reason for this is that the attraction between non-bonding electrons on oxygen, so there's two lone pairs of electrons on the oxygen of a water molecule, and the charge of the metal cation causes a shift of the electron densities in water. So the electrons, those lone pairs on the oxygen molecule, are attracted to the charge of the cation, and so therefore make the water more, the density kind of shift around. So this makes the OH bond more polar, and so therefore the water becomes more acidic. And the greater the charge and smaller the size of a cation, the more acidic it is. So like a sodium ion with a 1 plus is going to have, dissolved in solution, is going to have less of an impact on changing the acidity versus say like aluminum cations. So let's look at the effect of cations and anions in solution. So an anion that is the conjugate base of a strong acid will not affect the pH. So this is the idea of when you have HCl, right? So you dissolve HCl in water, okay? You get lots of hydronium ions. But the Cl minus, which is the conjugate base of that strong acid, it doesn't have any effect. It doesn't interact with water. You don't get a base out of Cl minus. But the anions of so an anion that is the conjugate base of a weak acid will increase the pH. It will behave as a base. Okay, so the conjugate base of a weak acid will have an effect. And a cation that is the conjugate acid of a weak base will decrease the pH. Cations of strong bases, of strong Arrhenius bases, will not affect the pH. This is the idea of, so when you dissolve a strong base like sodium hydroxide, NaOH, the sodium, or Na, if I dissolve a bunch of Na in solution and get a bunch of Na pluses, I'm not going to see any change in the pH. It's not going to affect it. It's not going to make it more acidic because of that. Other metal anions will cause a decrease in pH if you put more or dissolve more in there. When a solution contains both the conjugate base and a weak acid and the conjugate acid of a weak base, the effect on the pH depends on the Ka and Kb values. And this is actually, so our next lab is going to be looking at buffers, creating buffers in solution. So basically creating a solution, your blood is a natural buffer. Basically, you you work with a weak acid and a weak base and dissolve the conjugate acid and the conjugate base of those two substances. So basically, as you put in more acid, the buffer will utilize the conjugate base to basically try to keep the pH, or it not try to, it doesn't have a will, but it will hold the pH pretty close to the same pH as long as you've got enough of the salts present. And it'll be more clear as we do that lab next week. But let's look at some factors that affect acid strength. And I think this is actually a really useful table to kind of think of, especially like if you think of when you're taking an AP, when you're taking the AP exam, and you're trying to think through, okay, what's going to be an acid, what's going to be a base, if they just kind of throw it at you, kind of being able to predict trends. And so kind of knowing the trends using the periodic table is really useful. So the more polar the HX bond or the weaker the HX bond, the more acidic the compound is. So as you can see, going up a column, you're going to increase the base strength, and going down a column, you're going to increase the acid strength of those HX bonds. And then notice going from left to right, you're increasing in acid strength, and going from right to left, you're going to increase in base strength. Okay, so it's really, I would say, a really useful tool to have that kind of solidified in your mind. So if you came across one, you wouldn't necessarily have to have these memorized, but could kind of position them on the periodic table and predict what their properties would be in relation to their position on the periodic table. So acidity increases from left to right across a row and from top to bottom down a group. So what are the factors that are affecting acid strength? So oxyacids, so where you have an OH is bonded to another atom like Y. So in our examples here, we have chlorine and iodine. The more electronegative thing that the OH is connected to is going to be the more acidic compound. So chlorine is more electronegative than iodine, and so therefore you're going to see chlorine has a higher Ka. So we've got this table here down to the right. So we've got some Ka values, and the lower, or I guess, yeah, the larger the Ka value, which 3.0 times 10 to the negative 8th is larger than 2.3 times 10 to the negative 11th, the larger, then you get a greater acidity out of that. Another look here, so for series of oxyacids, acidity increases from the number of oxygens. So look at the Ka values as you go along. You're getting a low Ka value, it's getting higher, and then you have some strong acids. Another thing to consider are compounds that might have a resonance structure. So carboxylic acid is a very common organic acid that you come across. We use it, well, actually in Unit 2 in first year chemistry, we use a lot of carboxylic acid when we were making perfumes or different smells. So, but when it loses its hydrogen, so as an acid, it loses a hydrogen off of that O there. But once that oxygen is gone, you can actually have two different resonance structures. So that double bond, it could be on either one of the oxygens. And so when that occurs, it makes a conjugate acid that's more acidic because of that resonance stability. And the last little section, it's more just kind of like a real brief introduction, is regarding Lewis acids. So Lewis acids are things that accept lone pairs of electrons, and then Lewis bases are things that are lone pair donators. Okay, so Lewis acids are defined as electron pair acceptors, and atoms with an empty valence orbital can be Lewis acids. So the boron trifluoride here has a empty valence orbital, and so therefore it's classified as a Lewis acid. And then the ammonia is a Lewis base because it has a lone pair of electrons that can be donated. So anything that could be a Bronsted-Lowry base is a Lewis base as well. Okay, so that's it for chapter 16, and we actually will be having an exam next week, either Wednesday or Thursday. So I guess probably be in work on review.